All right, welcome. In this video, I want to talk about a couple different variants of Turing machines. So there are many different variants of Turing machines. Here are just a couple that we might talk about in this video. Multi-tape Turing machines, non-deterministic Turing machines relative to deterministic ones that are our standard version, probabilistic Turing machines, or even quantum Turing machines are another kind of Turing machine that have been discussed. And all of these different variants of Turing machines are different models of computation. And just like we've been seeing in this series of videos, there are different models of computation, might have different powers in the types of languages that they can compute. And so that raises just our standard question, which is what is the relative power among these different kinds of Turing machines? If any of them are more powerful than others, which ones might those be? And then just a quick little spoiler alert here, it turns out all these different kinds of Turing machines are of equal computational power, meaning if you want to talk about a Turing machine, you could talk about any one of these and you would end up having the same set of languages that could be computed. All right, so let's just start with a very simple a very simple variant of a Turing machine. Our variant of our Turing machine that we've been looking at so far, we might call it our standard variant or our default variant, has had a two-way infinite tape. But this isn't the only way we could define our Turing machine, and in fact, we can define our Turing machine to have only a one-way infinite tape, and that's the idea behind this variant here. We're going to call this a one-way infinite Turing machine, or a 1TM. We're going to say that this Turing machine operates the same way as the 2TM that we normally have, except that it is special, that it has no or there is a leftmost cell, I should say, and there are no cells to the left of the leftmost cell. And then also when we have this type of Turing machine, we usually add a special rule, which is if we try to move left from that leftmost cell, that is an entrance into the reject state. So we automatically reject if we try and move left from that cell. So this is a different kind of Turing machine than a two Turing machine, certainly. At first glance, we might think that a two-way infinite machine seems more powerful because it seems to have more cells, or that's not exactly accurate. It actually has the same number of cells, infinite cells, but there seems to be 2 degrees of freedom. We can go to the left and the right instead of just the right. Maybe that's beneficial to us in some way. However, it turns out there's really only 2 functional differences between the 2 machines, and I want to characterize these here. So in a two-way infinite machine, if a two-way infinite machine was trying to act like a one-way infinite machine, it would fail only in a certain case. That is, it wouldn't reject when it moved left from the first cell. It would move left, and there would be a blank there, and then, or it would enter into some kind of loop or erroneous actions that were not expected by the one-way machine. So if we could instead cause that two-way machine to do what the one-way machine was expected to do, then we could say that the two-way machine could simulate the one-way machine. And then in the other direction, we might also want to say, okay, what is it that the one-way infinite machine can't do that the two-way infinite machine can do? Well, the one-way infinite machine can't move to the left of the leftmost cell. There's nothing there, and it would reject if it tried. And the two-way infinite machine can move left there and can go to the little blank there or whatever it's looking for to the left there, and it may move back and continue its processing in a way that the one-way infinite machine would not. So again, if there was a way for us to have the one-way infinite machine be able to move to the left, even though there's no cell there, if there was some way we could do that, then we could say that the one-way infinite machine could simulate the two-way machine, because all of the other operations that our two machines can do are the same. When they're not in that leftmost cell, they can do everything else that's the same. They can move left, they can move right, they can read, they can write. They can do everything a normal Turing machine can do. So we can obviously simulate all those steps. It's only in these 2 specific cases where we're going to run into an asymmetry between our 2 models. So usually what happens when we have a variant like this, what we're going to try and do is show how we can simulate the other machine by focusing on these key differences and showing that, hey, how can we carry out these key differences? So I'm going to show how we can do that for our two machines here. So in this case, we're going to start with a two-way infinite Turing machine. And we're going to try and simulate a one-way infinite Turing machine. So the way we're going to do this is by following all the same steps as a one-way Turing machine. But when we get into that one case, moving left from the leftmost cell, we want to make sure that we can detect that case and then carry out what the 1TM would do instead, which is reject. So what we're going to do is, before we start our operation, our simulation of the machine, we're going to add a special symbol, one that's not in our alphabet, onto the cell to the left of our input. So you can think of what we're going to do is we're going to move left first. We're going to write this special symbol. I've used a hash in this case. And then we're going to move right again. So we're scanning the 1 again. We're back scanning the first symbol of the input. And then we're going to begin simulating the one Turing machine. Now that one Turing machine is going to do a bunch of stuff, and eventually at some point it might move back to this cell. It might try to move left from the leftmost cell. If that happens, we will be scanning our special symbol. So what we're going to add here is our special case. Should that symbol ever be scanned during our simulation, we will reject. Why? Because that's what the 1TM would do. So we won't continue simulating. If ever we see a hash, we reject. So this is sort of a simple idea. It's kind of the simpler of the two branches, but it shows how we can take any one Turing machine, one-dimensional or one-directional infinite Turing machine, and simulate it with a two-directional infinite Turing machine. So now we just have to do the other direction. That one seems a little bit harder. Now let's see why that is. In this case, what's going to happen is we are still going to have this leftmost cell, but we're going to want in our one-way Turing machine to be able to simulate moving to the left as far as we need to, because a two Turing machine might move to the left. We just saw that in our last machine. The first thing that it did was move to the left and write in the special symbol. So we're going to have to do something even more special in this case. What we're going to do is we are still going to use a special symbol here, because we don't want to accidentally move off of the left-hand side of our machine. If we did, we would reject, and that's something we shouldn't do. So we want to stop ourselves from doing that. So the first thing we're going to do is add this special symbol, but we can't just overwrite the first symbol there. That would change our input. So we need to move all of our input to the right, all by one cell. Now there's a couple ways that we can do this. One way we can do this is we can start on that first symbol and just write a hash, but when we do it, we remember whatever symbol it was, a 0 or a 1, and we move to the right, and then we say same thing. We will overwrite it with whatever we remembered, and then we will remember this cell and move 1 to the cell right. That's one way to do it. It's a little bit trickier because you have to remember everything as you go. There is another way where we could copy it from the right and move back. The goal at the end is always going to be the same, which is we just want to move all the symbols exactly one square to the right. Once we do that, if we just did that in general, we would probably end up with a blank here. And then we can write that special symbol in there if we wanted to. Okay, now this is an operation, I'm going to call it a subroutine, that we're going to want to carry out more than once in this simulation, which is whenever our two Turing machine that we're simulating moves to the left of the current leftmost symbol and we start scanning the hash, we're going to stop and we're going to say, oh, we actually needed a bucket here, a blank. So we'll stop, we'll pause, we'll move everything to the right, we'll put a bucket into that extra new square that we have. We will move the tape head to scan that bucket, and then we will begin simulating again. Now what that's going to mean is that we're going to use that subroutine every time we scan the hash. So anytime we might have to go to the left-hand side there, we will bump everything to the right. That when we use the subroutine, we pause the simulation of the Turing machine, and then we restart it back up again after we've simulated. In this way, we can make sure there's always enough spaces to the left. This is sort of a very opportunistic way that says, hey, as soon as I need a space, I make one, and only one. But if we wanted to, we could imagine in our original subroutine by padding with, I don't know, 15, 20, 100, however many spaces you think you might need. Of course, in general, you need to have a subroutine that's going to add more spaces if you need them, because there's infinite of them in that direction. We need to have some way to simulate that. But if in practice you kind of knew, hey, I'm probably only going to need 15 of these, you might put 15 in your simulation and then go ahead and simulate. Now, this is just meant to be, again, another proof idea showing how we can use a one-way Turing machine to simulate two-way directional infinite, even though we only have one-way infinite. And the reason is we technically have the same number of cells. We just need to move ours over enough to the right to make sure that we have cells on the left to accommodate our simulation. So with this proof, we've completed our very simple sort of back and forth proof. Again, we haven't done formal proofs here. I've done these pretty informally, explaining the key components or the key idea of the proof. But this shows that a one-directional infinite Turing machine and a two-directional infinite Turing machine have the equivalent power. And again, how did we show that? We showed that one could simulate the other and vice versa. And these simulation arguments are key to showing that two models of computation have equivalent power. So with that, I want to define another model, and that's going to be our non-deterministic Turing machine now. This is different than the deterministic one that we've defined, although a lot of the definition is exactly the same. So I will only highlight the key part that has changed, and that is the change in the transition function. And if you recall, when we defined non-deterministic finite automata, we've made the same change here, which is instead of having our transition function go from a state and a symbol scanned to just a state, symbol scanned, and moving left or right, we now have the power set of that particular cross product, which means we can have 0 possible transitions labeled for any particular state and symbol combo, and we might also have more than one possible transition, and that's where the non-determinism comes in. And maybe I'll just mention there's one sort of interesting power that non-determinism then can give us. It can write things on the tape that you might not, it can just sort of write non-deterministically things on the tape, meaning you can set it up to say write 0 star or 0 1 star on the tape, and it will be able to write any string it wants on the tape before, say, you start going. So one way that we interpret non-deterministic processing is to say that the first thing it does is it writes something on the tape, and then the second thing it does is it does a deterministic step where it now just processes using those symbols that it had written on the tape non-deterministically. Now that's something we're not going to look at in a lot of detail, but I did want to highlight that one of the ways we interpret the non-deterministic power of a Turing machine is to say, well, before any processing begins, we can imagine it just writing whatever it wants on the tape. Okay, so in a deterministic Turing machine, a couple videos ago, we talked about some formal definitions, and one of the things we talked about was a computation. We talked about accepting computations, and the one that I have displayed here is an accepting computation because it ends in an accept state. This was one that we did in one of our example computations simulating a language that was 0 to the n, 1 to the n. We just showed how this Turing machine, I don't have the Turing machine depicted here, just the computation, but this just showed the sequence of configurations that the Turing machine went through to arrive at the accept state at the end. And at the end here we see the accepting configuration has nothing written on the tape, so it also erased everything on the tape while it did that. So this is an example of a deterministic Turing machine's computation, and the thing that I'm trying to highlight here is that this is a single sequence of configurations. one configuration yields another in a deterministic. This is what we mean by deterministic, is that any one configuration following the rules of the algorithm, or in this case the Turing machine, will result in a next configuration and the next, and it will always be the same if you're giving it the same input. So a non-deterministic computation is going to be different than that. We like to think of it as a tree. So remember, I mentioned maybe writing something down on the tape. We could think of this as the machine deciding, should I write a 0 or a 1 on the tape? Now, the non-deterministic machine doesn't always have to use its non-determinism to write, like I mentioned in that example. It could use its non-determinism to move its tape head or do something else as well. But we can imagine what's going to happen when in a non-deterministic machine is that we're going to have branching that occurs from one configuration. So these are now representing configurations, these little nodes in my tree here, but this might be my initial configuration, and then non-deterministically I might choose to branch to the left or the right by choosing to maybe move to the left or the right, or maybe choosing to write a 0 or a 1, something like that. That's where the non-determinism can come in, or maybe just choosing to change state like we did in the non-deterministic finite automatas. These are all things that we could do non-deterministically that might change our configuration, and we might have this non-deterministic, we might sometimes think of it as a choice. Which of these configurations should we go into? And then if at each configuration I have more non-deterministic choices I can make, then I might have this branching structure. Of course, we call this a tree that of configurations, and we might call this a computation tree if we'd like, instead of just a single sequence of configurations. We've now got this tree. So this is an important way to understand how non-deterministic computation occurs. But I've also depicted here with the red and the green here the possibility of accepting and rejecting computations. Now I've made a very shallow tree. Non-deterministic computation tends to be a very deep tree. This is just an example tree, but we can imagine there being some at the leaves, because remember, a computation always ends when we enter one of these states. We're either going to be in accept or reject states, and it's possible that some of these go on forever as well. I should mention that as well. But in this case, I've depicted sort of one where we always halt and we either enter into an accept or reject state, and that raises the question, well, how do we know if a non-deterministic machine accepts or rejects? And that's another part of the definition of non-determinism, is that a non-deterministic machine is going to accept if any configuration in this computation tree is an accepting configuration. That's why non-determinism is considered to be sort of a magical power, and I say magical to mean not physically realizable, and that means not something we could build in the physical world as a physical machine. So this idea, a non-deterministic Turing machine, the way that we think it operates in a theoretical sense, is impossible in a real physical sense. We don't know how to create it. However, we do, and we're going to show that, spoilers in this video, that know how to simulate this non-deterministic Turing machine with a deterministic one, which means that even though we cannot create the magical non-deterministic machine, we can create a realistic deterministic machine that at least carries out in some essence the same steps of the non-deterministic machine. Of course, it cannot do non-deterministic things, but it can act as though it can do non-deterministic things in a deterministic manner. And that's going to be the goal of the rest of this video, is we want to show that a non-deterministic Turing machine is of equivalent power to a deterministic Turing machine. And that means we need to do our mutual simulation argument. Now, it's easy to show that every deterministic Turing machine is a non-deterministic one that basically just never uses its non-deterministic magical power. It's like, I have access to the magical power, I'm just never going to use it. Then you're a deterministic Turing machine. So it's easy for us to show that we can simulate a deterministic machine with a non-deterministic one. We just never use the magical power, the non-determinism. So we have to flip it around the other way. We need to be able to show that a non-deterministic Turing machine can be simulated by a deterministic one, and that's going to be our goal here. So, interestingly, to do this, all at once. It's kind of a pretty complicated proof. And instead, to make it a little bit easier on ourselves, I'm going to break it into two proofs by adding an intermediary kind of Turing machine. I want to show that a non-deterministic Turing machine is simulated by our standard two-directional infinite Turing machine, the default model that we've been using. To get all the way there, I might have to do a lot of interesting steps to make that work. So instead, I'm going to use an intermediate Turing machine. And this one's going to be called a K-tape Turing machine. That means it's going to have more tapes than just one. So we just showed that if I have a single tape that's one-way infinite, that's no more or no less powerful than two-way infinite. And what we're going to need to show here is that having an extra tape, a whole extra tape, not that a K-tape Turing machine kind of looks something like this, that showing that instead of just having one tape that's two-way infinite, that having two or three or K, however many there might be, that is no more powerful than just having one tape. And we're going to have to show that, but for the moment, let's accept that that's true. And let's also imagine how these K-tape Turing machines might operate. They're a little bit different. I'm not going to give you the formal definition of a K-tape Turing machine. Instead, maybe I'll leave that as an exercise. It's pretty easy to manipulate the normal definition of a Turing machine to come up with a Turing machine with K-tapes. The only difference is we're going to have more than one tape, so we're going to have to reference that in some way. Now, one thing that's interesting about the K-tape Turing machine is it also comes equipped with K heads, which means at any one point we will be scanning K symbols from our K tapes, and all of those symbols can tell us what we want to do now. Okay, and then also we can write to all of those K positions, and we can move all of those tape heads. So what does that mean for us? That means we're going to have a lot more operations that we can be carrying out as a result of whatever it is that we're scanning on all these K tapes. Now, the other thing that we can do with these K tapes is we have to decide, well, what are we storing on these tapes? Now, usually these extra tapes are auxiliary tapes. The input is still stored on the first tape. Usually we might sometimes call that especially the input tape. But the rest of the tapes usually start out empty with nothing on them, unless we have some very special K-tape Turing machine that there's some reason why we have these extra tapes that we're putting extra inputs on there, maybe whatever that might be. We'd have to define something around that. That's why I'm being a little bit cagey about it, because I haven't actually said what that might be yet. But in general, our K-tape Turing machines, we assume those extra tapes are just auxiliary tapes. Think of them as helper variables or extra variables, local variables that you might be using in your K-tape Turing machine. You might want to write something down on these extra tapes to remember them for later, so you can look them up later. That's basically what they're going to be used for. That's what we're going to use them for as well, to store some extra stuff, that working memory, if you like. While that might allow us to keep the input tape untouched, maybe we don't do anything to it so that we can go back and copy it down again later. Again, that's something we are going to use our K-tape Turing machine for. So these extra tapes, these auxiliary tapes, typically start out empty, but we might be using them for special purposes as we go. So our goal, as I mentioned, this K Turing machine is going to be an intermediate between the two. So we're going to start with a non-deterministic Turing machine, and we're going to show that it can be simulated by a Turing machine that has K tapes. And then I'll complete the proof off by showing, okay, and now I'll show you how a K-tape Turing machine can be simulated by a standard default model one-tape Turing machine. Okay, and then by the transitivity of this simulation, if A can simulate B and B can simulate C, then A can simulate C. That's sort of the idea here. And so we've got this transitivity operation here. By putting this intermediate K-tape Turing machine inside, we're going to make the two proofs a little bit easier, and then that's going to allow us to show our ultimate proof that deterministic Turing machines can simulate non-deterministic ones. Okay, like I mentioned, we will begin by arguing that a non-deterministic Turing machine can be simulated by a K-tape Turing machine. So we're going to start by assuming we have some non-deterministic Turing machine. I'm going to call this one M1. And we're going to simulate M1 by doing a breadth first search of the computation tree of M1. So I already mentioned that we have this potential tree of configurations that we need to search, and we are selecting a breadth first search, not a depth first search, because it's possible that some of the branches of our computation tree have infinite depth. So if we started to go down them, it would go for infinity before we would never reach the end, and so we would never be able to stop them and search any other branches. And since we want to be able to search all the branches, including ones that have infinite depth, we want to do a breadth first search. That means we're going to search only down to one depth, and then the next depth, and then the next, and so on. Okay, so this is going to be a breadth first search of the computation tree, and then we're going to do it with a KTM, but specifically I'm going to use 3 tapes. So I'm going to call it a 3-tape deterministic Turing machine, and we'll give it a name M2 just so we can be formal about it. Okay, so what are we going to do with our 3 tapes? Well, on tape 1, we're going to have the input. I already mentioned the first tape is usually where the input string is stored. So that's all it's going to be for. We're going to put the input string on the first tape. That's where it originates, and we're never going to change it. What we're going to do instead is we're going to copy this string to tape 2 whenever we need to, including right away. The very first thing we're going to do is copy it to tape 2. Tape 2 is going to be our simulation tape. So this is where we're going to actually be carrying out computations as we go. Okay, this is going to be like our main tape, as though we had a single tape Turing machine. And then on tape 3, we're going to keep track of which branch we're on, which of the non-deterministic branch we are currently simulating, and that's so that in our breadth first search we can remember which branch to be on, but also when we arrive at a non-deterministic choice for our machine M1, we cannot simulate a non-deterministic choice in M2 because M2 is deterministic, so it cannot simulate non-deterministic choices. So when we get to a non-deterministic choice, we're going to check tape 3 and see, okay, which branch are we on? If we were in that branch, what would the non-deterministic choice have been? And then we will carry that out. Now, that's what I want to talk a little bit more about here. How is it that we're going to be able to do this? So how do we keep track of which branch we're simulating on? So imagine now that we have to keep track of all of the branches, we're going to use symbols in our tape alphabet to do that. Now, very simply, if we just had 2 branches, branch 1 and 2, here I've used 1 and 2, but if we had 2, we often use binary, so we might just have 0 and 1. But if we had 2 branches, then our branching factor here, B, would be 2. Okay, and that was depicted in the example that we had earlier, a binary tree, where non-deterministically we only ever branch, say, left or right, or 0 or 1. But in general, we could non-deterministically do all kinds of things. So what we're going to do is we're going to look at our machine and figure out what the branching factor is. You can usually do that by looking at the description of the machine. And once you know what that branching factor is, we're going to make a new special alphabet. It's going to be a sub-alphabet of our tape alphabet. And we're going to, in this case, I've just made the numerals 1 up to B, assuming that those numerals existed. But we can use any symbols here we want. We could use a special subscript symbol like B sub 1, B sub 2, B sub, and so on to be our symbols here. All that matters is that we have B symbols so that we can start writing strings of these symbols on tape 3. Now what we're going to be doing is we're going to use one of these symbols to encode each of the branches or the choices that we might make in one of our branches, left or right, or of the B possible choices. And then what we can do is we can depict any branch of length D with D characters. So what we're going to do is we're going to write down D possible, D being here for depth, D of these gamma B characters on tape 3, and that's going to write down the branches that, or the choices that we're going to need to carry out this branch. Let's for a moment think of this as just being our binary tree. So in our binary tree, we have at every point, every node, we can make a left or right choice. If we want to encode one of these branches, then we can encode it as a series of left and right choices. We can say left, left, right, and then that is technically a string over an alphabet that encodes that branch, and that would technically be a string over lefts and rights. We could call it L's and R's, or we could make it a binary string over zeros and ones, where we just have 0, 1, 1, 0, 1, and that encodes one of our branches. So 0, 0, 0, 0, 0 would encode the leftmost branch, 1, 1, 1, 1, 1 would encode the rightmost branch, and so on. So in this way, we can encode every single branch of size D. And we could do that with D characters. And that's exactly how we're going to do that. So when we simulate our non-deterministic choice, whenever we're simulating our non-deterministic machine M1, and we get to a point where it says, okay, now make a non-deterministic choice where we either have to go, to the left or the right, branch 1 or branch 2, we go look at the characters stored on tape 3, we figure out the right branch to pick, and then we simulate that branch on tape 2. Remember, tape 2 is where we're carrying out the simulation. So now that we have that's sort of a subroutine that shows you how we're going to be carrying out that non-deterministic simulation, now we can show you how we do the breadth first search. So the breadth first search, we're going to start with, say, depth 1. We don't have to start with depth 1. We can pick any arbitrary depth to begin with. We could pick depth 1,000,000 if we wanted to begin with. The only thing we can't do is we can't just say do a depth first search, because a depth first search is going to possibly get us caught in one of those infinitely long branches. But if we say start with depth, any finite depth, say maybe D is 1,000,000, then we guarantee that we're not going to dive into those infinite branches. We'll cut them off after 1,000,000 steps. But that might also allow us to find all the accept states that we're looking for. Remember, all we're doing here is searching for an accept state. So how do we do this? Again, I'm going to say let's start with D equals 1 for our proof, because usually in a proof we're not actually carrying out these simulations, so we're not as worried about the efficiency. So in this case, we'll start with depth D equals 1. I mentioned first thing we're going to do, copy the input string to tape 2. Then we're going to write the first string of length D over our branching alphabet on tape 3. Okay, so that might be 0. And then we're going to simulate M1 D steps. Now, if we did start with D equals 1, that means only one step. So if it immediately accepted, good, we've found it. If not, then we haven't found it. So at this point, it says if an accepting configuration is reached, we accept, great. But if not, we continue. So if we've simulated D steps and we haven't found an accepting configuration, we move on to step 4 that says, okay, erase the contents of tape 2 and write the next string of length D over the alphabet on tape 3. And then repeat these steps again. So simulate the D steps again with the new branching alphabet. So maybe we've got branching the new branch 1. Okay, so now it's saying take the right branch instead of the left branch. But maybe then we have now we've still not found an accepting configuration. So then what we're going to do is we're going to increase D. So now we are no longer going to have depth D equals 1. We'll try depth D equals 2. And we'll repeat the whole thing again. We'll start the whole thing all over again and look for an accepting configuration at depth 2. If that doesn't work, try depth 3, depth 4, depth 5, and so on. We'll keep doing that until we find an accepting configuration, or we go on forever. Or we arrive at all rejecting states, in which case we can also reject. That's the only way we can reject, is that if every single branch rejects, then we can reject. Otherwise, we're going to keep infinitely searching for those accept states. That's something that's okay for us to do in this simulation. So what this has allowed us to do is show that our non-deterministic Turing machine can be simulated as long as we have 3 tapes we can use. Remember, the first tape just stored the input so we could copy it down every time we did a new simulation. The second tape is where we did our simulation, and the third tape encoded our non-deterministic branches. So now we need to complete our proof by showing that a three tape Turing machine can be simulated by a one tape Turing machine. All right, so I'm going to do it slightly more generally. I'm going to instead show that a K tape Turing machine can be simulated by a single tape Turing machine, or our standard default model. So again, we're going to start out with just any arbitrary K-tape Turing machine. We're going to simulate it with a single tape. So what do we need to do? We need to simulate K different tapes on the one tape. That means we need to store all the contents of the K tapes on one tape. That seems maybe problematic. And we must remember the locations of all of our K tape heads, because we only have one tape head that's going to be doing a lot of scanning back and forth, and we're going to have to remember where the other tape heads are so that we can simulate their actions. So those are the two main things that we're going to have to focus on in our proof. So the first thing is going to be, how are we going to keep our multiple tape contents separated or available for us to simulate on a single tape? Luckily, by adding multiple tapes in, we haven't actually added in more cells. We still have an infinite number of cells. And so what that means is we should be able to partition the tape that we do have in nice ways that allow us to still have potentially infinite cells on any one tape, while maybe not ever actually having infinite cells on any one tape. And that's what we're gonna do here is going to be very similar to how we began this video, by simulating a one-way infinite Turing machine. Because remember, in that way we had infinite only in one direction, but we were still kind of able to simulate infinite in the other direction. And that's what we're going to take that same idea here. So the first thing we're going to have to do is we're going to have to separate our tape contents in some way. Once again, let's go pull our hash symbol out, or some other special symbol if that's already in our alphabet. And we're going to use that symbol to separate our K tapes into different sections of our tape, of our one single tape. Now we'll assume we're using our standard K-tape model, where initially the input is written on the first tape and all of our other tapes are empty. So what does that really mean? At the beginning, we're going to have to start by adding a bunch of hash symbols to our tape. Our input is already on the tape. We'll probably go to the end of the input, because that will be maybe the end of the input tape, the first tape. And then we'll put a hash, and that will be mark the beginning of the second tape. And then we could, if we wanted to, put some blanks in there, because we know that at some point we're probably going to have to be simulating and doing something on that tape. But at the minimum, maybe we'll put one blank in there, and I'll come back to that in a second. And then we'll put another hash, and then maybe another blank, and another hash, and another blank, and another hash, and another blank, until we've got all K tapes set up. The last tape can be infinite in the right direction, right? So we'll have a hash, and then all the rest of the tape can be just the last tape. But then once we have those K, technically K minus 1 hashes will make K tapes for us, then we can begin our simulation. Although there's one other thing that we need to remember, which is we need to remember where the tape head is for each of those tapes. And we need a strategy for doing that. And the way that I'm going to do that, or I'm going to consider doing that here, is just by making a special dot on top of every one of our symbols. So let's say our current tape alphabet is the binary alphabet, 0s and 1s, but it's also got buckets, or blanks, of course, that has to be included. So we're going to add 3 new symbols to our tape alphabet for our simulation tape. It's going to have 0 with a dot on it, 1 with a dot on it, and bucket with a dot on it, or blank with a dot on it. And what that is intended to signify is where the tape head is for that tape. That way, when we move to, say, the second tape, and we start scanning between those 2 hash marks that tell us where it begins and ends, we can find where the tape head is by finding the hopefully only one symbol that has a dot on it. Okay, and that's how we also have to set up. So I said I'm going to come back to those blanks. When we add the blanks in, we technically want to add blanks with a dot, because we know that our tape head will be scanning that first blank in each of our additional tapes. And so if we're going to add a single blank in there, we should add a single blank with a dot. If we're going to add multiple blanks in there, we should still only add a single blank with a dot, and all the others can just be normal blanks. Okay, so again, this is setting things up. Now we can imagine simulating for a while, we're going to have maybe non-blank symbols in there like zeros and ones, then we're going to want to have to be able to signify that our tape head is scanning them as well. So for any symbol in our tape alphabet, we're going to have to make one of these special extra symbols in our tape alphabet with a dot on top of it. The other thing we're going to have to do in our initialization phase is make sure that there's a dot on top of the first symbol of our input, whatever that might be. Again, if our doing the binary alphabet, it's a 0 or a 1, but it could also be a blank as well. Remember, we could have an empty input, in which case we need to put a dot on that. So mark off all of our K tape heads by putting dots. Okay, now we also have to worry about what happens when we run out of space. All we've made is one space for all those K tapes. What happens if we run out of space? Well, if any of our tape heads is going to try to move to the right into a hash mark or to the left into a hash mark, then we're going to go out and get our special subroutine that we already worked on at the beginning of this video that just shifts everything to the right, or technically to the left, whatever. You can make multiple versions of these subroutines. You can make special, more complex versions. But the simplest version just says move everything to the right, make an extra bucket where you need it, either before the hash or after the hash, depending on what you're simulating here. Once you've moved everything to the left or the right, and you've made your extra special bucket, then go back to simulating. Move the tape head where it needs to be. Okay. All right, so how does simulation work? Okay, we're going to have to simulate all K of our tapes. We have to do that all with one tape and with one tape head. So what are we going to do? Well, the very first step we do in our simulation is we scan across all of our K tapes, looking for those K tape heads and remembering as we go what they are scanning. And that means branching in our states quite a lot. So remembering the first one, what are you scanning? Oh, you're scanning a 0. Okay, second tape head, what are you scanning? Oh, you're scanning a 1. Okay, third tape head, oh, you're on a blank. We keep doing that for all K tape heads, and now we remember what all of them are. That allows us to access our transition function and say, okay, now that we know what we're scanning on all our K tape heads, we know what we should do. And now that we know what we should do, we will go and do it. Again, our tape head's going to scan across all K tapes. It's going to go back to finding those K tape heads, and it's going to say, for each one of those K tape heads, I know what you're supposed to do. You're supposed to write a symbol. So I'm going to overwrite the current symbol with a new symbol. And then also you're probably going to move left or right. So I'm also going to have to move that little dot symbol to the left or the right for you. I'm going to do that for all K of my K tape heads. So I'm going to go and do that. After I've done that, I will have updated the configuration that we have encoded on our tape exactly one step of our K tape head. So that means every time we're going to do one step of our K tape Turing machine, we're going to have to move that tape head back and forth a whole bunch of times scanning. Okay. Now technically probably two or three times you're going to move back and forth, because you'll only need one pass to read all of the tape heads. You'll probably need one pass with a little jiggling back and forth probably to do all the writes, and then you have to rewind back to the beginning or do something, maybe to do a reset there. So it might take you 3, if you can't do it cleverly, in 2 passes back over the whole tape contents. Okay, so it's going to be a long process to simulate. Okay, now what else are we going to do? We're just going to keep track of the states as we're going. So we do that with our own states. Okay, so we don't actually have to encode those on the tape anywhere, but we're going to just keep track that if the transition we were following would have led to an accept state for our K-tape Turing machine, we'll just follow that into an accept state of our own. Likewise for reject states. Okay, so that closes the circuit for us. That completes it. That shows now that non-deterministic Turing machines are of equivalent power to deterministic Turing machines. And we also added in there a third model if we wanted, K-tape Turing machines if you want. So now we can use K-tape Turing machines also as a potential model of Turing machines. And this showed, maybe interestingly, that non-deterministic Turing machines are of equivalent power computationally to Turing machines. But it raised a very interesting problem, which is when we started simulating non-deterministic Turing machines with deterministic Turing machines, we found that they take exponentially longer. Now I'm saying longer here as though in time, but they actually have exponentially more states, and it actually turns out the number of configurations that you need to go through also turn out to be exponentially longer. One way we can actually compare that is if we remember our deterministic computation is just a sequence of configurations, whereas the non-deterministic computation was a tree. Well, there are exponentially more nodes we can store in a tree of a particular depth than a sequence of that same length, and that's the idea here. So this raises this important question, which is this necessary? When we simulate a non-deterministic Turing machine, is it possible for us to do it without taking exponentially more time or exponentially more states? And the answer to this question remains an open question. This question was posed over 50 years ago in 1972, and it founded a whole other field of study called complexity theory when it was posed, and is still kind of famously known today as the P equals NP problem. Okay, and to sort of decode that equation a little bit, P means polynomial time on a deterministic Turing machine, and NP means polynomial time on a non-deterministic Turing machine. Okay, and the question is, so in the terms that we put here today, if you have a polynomial depth tree, non-deterministic tree, can you simulate that with a deterministic Turing machine that only has a polynomial length sequence of configurations? If you could show that, if you could prove that that was the case, you would have proven that P equals NP. This is something that many computer scientists, including myself, think is probably not going to ever be proven true. Instead, most of us believe that P is not equal to NP. But again, no one has proven that either, and it is a central open question to complexity theory and has driven over 50 years of research in that area. So this is a question we still don't know the answer to, and we haven't in this series of videos focused on complexity. We have only focused on computability. What can we compute? Can it be computed, yes or no Boolean, not how long does it take to be computed, which is now sort of a quantitative measure. That's what complexity theory is focused on. And I have a few videos on complexity theory in my algorithms sequence. You can check them out there. So I want to talk about other variants of Turing machines then. We've shown that a non-deterministic Turing machine is equivalent to a single tape Turing machine. But what other ones? Well, we showed that a multi-tape Turing machine is also equivalent to a single tape Turing machine. We could also define now what we might call a multi-head Turing machine. It only has one tape, but it's got multiple heads, so you don't have to be scanning back and forth all the time. Think how useful that would be for some of the languages that we've been looking at, like checking to see if two substrings are the same. We've had to scan back and forth to do that. We could just have two heads that move in lockstep in the two sequences we're trying to look for. Ooh, that would be so much more helpful. Turns out that's equal in power as well, so that's something we can use as well. Probabilistic Turing machines. These are a realistic version of a non-deterministic, or maybe more realistic. Some people might have a philosophical argument about that, but a non-deterministic machine, we said, was kind of magical. It can find that accepting configuration if it exists, even if there's only one of them out of an exponential number that it needs to search. Well, what a probabilistic Turing machine says, well, is if at least half of them, well, that's one definition. Well, let's use a different definition. If at least a third of our branches end in an accepting configuration, then we'll say that we accept. That means our chance, if we just randomly picked a path instead of non-deterministically magically picked it, we just randomly picked a path, our chance of finding a good path is good enough to accept. That defines a probabilistic Turing machine. That seems like it might give us more power. In a computational sense, it doesn't. It doesn't. We can simulate it in the exact same way we just simulated non-deterministic Turing machines by keeping track of every branch. In this case, we'd have to keep track of the probabilities of each branch. But if we keep track of the probabilities, we should be able to answer our question yes or no, would that machine accept? So this is no more or no less powerful. And then I won't go into a lot of detail, but in the 80s, they defined a new kind of machine called a quantum Turing machine, which is the foundation of quantum computation or quantum information theory and quantum computers. And there was, for the first time, a tantalizing question. Maybe quantum computers could do something that traditional, what we call classical computers now in this context, couldn't do. Is there something they couldn't do? And it turns out no. We can simulate a quantum Turing machine with a deterministic single-tape Turing machine as well, meaning that computationally they are no more powerful. Again, all of these questions do not answer the question with relation to complexity theory, which is, can we do things faster on a quantum Turing machine? And the answer to that still sounds like it probably is a yes for at least a small subset of problems. Quantum Turing machines are faster. And for that matter, probabilistic Turing machines are also faster as long as we're willing to accept some chance of error on some of our problems. So these are some interesting things. Again, if you're interested in that, explore complexity theory in more detail. So that's going to leave us with a final definition I just want to give you today, which is the idea of what we call Turing complete. Now, you may hear of this phrase out there in computational discussions. You might say such and such is Turing complete, and what that means is that model, usually we're using it to describe a model of computation, is equivalent to a Turing machine. So we've just shown that a whole bunch of different kinds of Turing machines are equivalent to a Turing machine. Those ones maybe are not super surprising. But in my next video, I'm going to show you a bunch of other models of computation that are also Turing complete, that is equivalent to a Turing machine in computational power, some of which are a little bit surprising. All right, thanks a lot for watching, and we'll see you in that next video.